Okay, welcome to the first day of Equilibrium. So, I was really hoping that we were going to be back at school for this, but apparently not. So, we're going to soldier on and do our best, thinking more towards next year. I will type out an announcement, so in case you want to go over this again for your midterm mark, which is due April 20th. That's a Monday. I'm not, to be honest, I don't know if they haven't said if it's like 9 a.m. April 20th or 3 p.m. April 20th. So, what we're going to do, because there are people who maybe did not bring their stuff home to get the rates unit stuff, to have an assessment for that is going to be a little bit tricky. So what I'm hoping to do, and I don't know how to do this, so I do have to practice. I am hoping to post something that is going to be a Word document. So it was a simple assignment that goes with this lesson on D2L. And then you're going to use like assignment or something or Dropbox. And then when you do that, when you put the assignment back in there, then I can use my Apple Pen and write right on it and give you feedback and send it back to you. So technically, I don't have to print it off. And then, how do I get you feedback, right? Like that's a nightmare. And obviously, you want feedback, of course. So that's what I'm going to try to do. What that means is, so this unit has a lot of math in it. So then how, to make you type out math, what's that going to look like? That's crazy. What I recommend that you do is get the app called Turbo Scan. And Turbo Scan it is so easy. Take a picture of your written work and then it automatically turns it into a PDF, which is easy to upload. It does not take a lot of space either. So you don't have to worry about these big documents like how do I get that to Mrs. Todd? And then again, I'm hoping to use a Dropbox. If I can't get it to work, then what I will do is you can just email it to me. But that's really not what I'm hoping to do. So because I want to make sure that it's going to work, then what I would like to do, I'm going to post the assignment and then make it, and then I'll extend, like I'll have the due date Sunday at midnight. I want to set a due date again so I can see how that works. If you are sick or if you are working or taking care of others or whatever, and you have a situation, please let me know. If you have other people in your house who are in different grades, they are not getting a midterm mark. So it's really just graduating students that I have to put a midterm mark in, and there is a deadline for that. So if you are concerned about what your mark was, then you want to make sure that we address that, okay? So then once that simple assignment, I've worked out the kinks with that, then there will be an assignment posted next Wednesday, and then there will be, which is the 8th, and then some kind of quiz, which really is an assignment on April 17th. So that April 17th one, so that's next Friday, that will be an important day again because your marks are due on the Monday. So, if it's just a small quiz, maybe a day's worth is good enough, or maybe I'll make it 2 days. We're really trying here to do what's best for you moving forward. Obviously, some of you need this mark to get into university. Hopefully the universities are going to take into consideration, but they haven't really given us much direction. So we're really trying to do the best we can. Okay? So I hope that works. Please remember, if you did not bring your textbook home, if you scroll all the way to the bottom on the announcements page, it's the first announcement. You can get a PDF version of our textbook as well. Then it goes along with the notes that are already posted in D2L, which you can print off. So this is 7.1. It is a PowerPoint, and then hopefully I can make one video and switch to 7.2, and then that's more of the math. So this is more of the theory behind equilibrium. Okay, so equilibrium is unique to you guys because we really have only dealt with, sorry guys, see already, I don't know how to use this. Okay, so in the last unit, we and previous to now, we've looked at reactions where we're considering what's the reactant chemicals. Last unit, we wrote a rate law. Rate equals the equilibrium or the rate constant K, and we looked at the concentration of the reactants. How much reactants we had, the size of the K. If it was large, that meant the reaction was fast because you're multiplying, and when you multiply big numbers, you end up with a big number, which means you end up with a big rate. Conversely, if you multiply by a small number, then you get a smaller number, making the rate smaller. Okay, so normally we would, or so far in your chemistry lives, we've considered that you have reactants that make products. But now we're going to consider reactions that actually will go in what we call the reverse direction. So there are plenty of reactions that actually have a competing reverse reaction. And that can be frustrating because frustrating in a practical sense. Like last year we talked about percent yield. Some of the when you have a reverse reaction, we consider that to be a competing reaction, and it can actually affect the yield if you're looking for the products in one of the directions. So then if we're considering now the reverse direction, that means that the rate law is now you're going to call what you would have called before the products. Now they are the reactants, and now you're going in a reverse direction. So we're going to use a double arrow, an arrow like you're used to, this one going forward, and then a new arrow going backwards. So eventually what happens is, you can sort of think of it like the collision theory. If you put in a lot of reactants, they collide, they make products, and then the reactant concentration goes down and the product concentration increases, which again we saw in the last unit. So then if the product concentration increases, now those product particles, they can collide, and then the reaction goes in the reverse direction. And eventually, where the forward reaction equals the rate of reverse reaction, and when it is in that balanced state, that's called equilibrium. So equilibrium, by definition in chemistry, is when opposing changes are occurring simultaneously at the same rate. Those of you that are biologists, we call this in grade 12 eubio, homeostasis. There are plenty of feedback loops in our body in order to keep our system sort of around a constant level. Okay, so equilibrium is achieved when opposing changes are equal. So what that means is the rate of forward reaction is equal to the rate of reverse reaction. So again, we're going to use this double arrow. So to be honest, if you are a kind of person who likes to type, it really depends on what version of Word you have, to be honest. So this arrow you might find, or you might get this arrow as well. So you can do full arrows. I don't know why my pen doesn't like to do this way. Oops, no, that's the one that's there. My pen does like this way. To do this one is harder for me to do. I know you can't see me trying to do it, but so it really doesn't matter. All of those mean the same thing. So when the reversible arrows are not equal, then that's going to indicate one direction is favored over the other, which we'll talk about when we do Le Chatelier's principle, or 7.3 in the next lesson. Okay, so observable macroscopic properties of a system at equilibrium are constant. So things that you can see and easily measure, like color, pressure, concentration, pH. If the forward and reverse direction is occurring at an equal rate, then all of these things should be constant. Equilibrium can only be reached in a closed system, which makes sense. If you're inputting something, whether it's matter or energy, it can influence the system and, of course, make the equilibrium shift or favor one direction over the other. So when we do Le Chatelier's principle, we'll talk about stresses. So how you can stress an equilibrium. And the whole point is it always wants to get back to its constant level. When you have equilibrium, microscopic properties are not constant. So we cannot see reacting particles with our eyes, but they are always changing into products. And then once there's enough product particles to start colliding, they are going to reform the reactants. So really, it's the same reaction principles we've talked about before. Now we're just going from left to right. No, from right to left instead of left to right. Okay, so the overall concentration of reactants in products is not changing with time because the forward and reverse reactions are occurring at equal rates. If nothing is happening, then we call that static equilibrium, which is not chemical equilibrium, and I'm never going to use that word again. Okay, so really we are considering when you have reactions that are still occurring, but the forward reaction, or how fast products are being produced, is equal to the reverse reaction, or how fast those products are being consumed. This is a graph. This is a graph to represent what is occurring in a reaction. So we have done concentration and time graphs before. So I can't cover it up without you can't see my hand. So if you look to the left of the dotted line, so past the dotted line, it says concentrations are constant from this time on. So that is where equilibrium is established. The lines are level or plateaued. None of them go to zero. So one direction is not being favored over the other past that dotted line. In the beginning, just like normal, the reactant up here, as written, starts very high, and the product down here, as written, starts very low. And then over time, they start to react. The reactant particles start to change into the product particles. And then when the lines plateau past that dotted line, that's where equilibrium is established. Neither of them is changing in a macroscopic way. Microscopically, the reactions are still continuing. Okay, so what I'm going to do is basically label the graph, okay? So when reaction starts, there is a high concentration of reactants and a low concentration of products. So if you want to put a 1 on your graph, oops, that was fast, sorry. There, so that's really essentially what we did in the last unit. You guys drew concentration time graphs representing the change. And then what happens is then now we've got a high concentration of reactants, and the products now are starting to change and increase as well. So initially the forward reaction, which is what you're normally used to, is greater than the reverse reaction. So the product is increasing and the reactant concentration is decreasing. So when you draw this arrow, we're not going to draw an equal arrow because they are not occurring at equal rates. The forward reaction is greater. How much greater? We don't really know yet. When we get to 7.5, we'll look at quantitative changes in equilibrium systems. But for now, you just want to show me that you know that there is a larger forward direction. So how large should it be? Again, just make sure I can tell. My top arrow here, which is the forward direction that you're used to, like reactants and products, has a much, much bigger size than the bottom arrow. So however you choose to draw them, if you prefer to draw the full arrow size, that's fine. Just make sure your forward arrow is much bigger than your reverse arrow. Okay, so then if this was a one directional reaction, then the reactant line, the red line would go all the way to the bottom, and the product line would keep increasing until a certain point when it didn't. But you can see again, once again, that these lines at the dotted line start to level out. Okay, so then that means then so you've got initially here at number 2, we've got products starting to be increased. So then eventually the products is going to become high, the concentration. So more products are reacting to produce reactant molecule. So then there are more products available to react to produce the reactant molecules, which is the reverse direction, which we have not considered before. Okay, so right about there where it's not going to zero, starting to plateau, now you're getting the other direction. Okay, so the products are starting to decrease and the reactants are increasing. So again, make your arrow, reverse arrow big and your forward arrow smaller. And then where you have forward and reverse reactions occurring at equal rates, the concentrations don't change, or the lines on the graph level out or plateau. Okay, and so now you want to make sure your double arrow has equal size arrows. Okay, so there, equilibrium is evident in the plateaus. Concentrations are not macroscopically changing. We cannot see it with our naked eye. And the reactants don't go to zero. The reactants are not completely converted into products. Okay, so let's see if I can get to this one. Sorry, I just want to check and make sure. Okay, let's give it a try. Okay, so when you have an equilibrium law, so that means that this is like the mathematical expression we're going to use in almost every single question we do, whether it's intro to equilibrium, the next topic is solubility, or the next topic after that is acid and base equilibrium. So Goldberg and Wage independently proposed the law of mass action, or the law of chemical equilibrium, that if you have a system at equilibrium, by definition, then that must mean that there is a constant ratio between the reactants and the products. So we call that KEQ. Just see something here. Okay, we call that KEQ. And so you can see here that KEQ is going to be similar to the rate law, but there are some differences. So we have the concentrations and we have exponents, which we experienced in the last unit as well. But now we've got a fraction, because we want to include not only the reactants this time like we did in the rates unit, now we need to include the products as well, because by definition there has to be a constant ratio. So there are some products and there are also some reactants in the reaction. Okay, so if you look here, you can see you have, you know what, I'm just going to have to write it out, which is no big deal. Okay, so for the reaction, I'm gonna have to write at the top. When I go to the pen, it sort of screws up a bit. Okay, so when you have the reaction at the bottom there, and you can see, if you've printed the note off, you can see it on your sheet, easy peasy. So it says KEQ, and it's got C and D. So when we do KEQ, pick a different color, no matter what, no matter if we're doing pressure, if we're doing concentration, if we're doing acids and bases, whatever, it's always going to be products over reactants. So tonight when you go to sleep, you need to say that over and over again until your caregiver comes in and says, can you please be quiet and go to sleep, okay? KEQ or KA, KB, KSP, no matter what K we do, is going to be products over reactants. So here we've got our products are C and D. So I put them on the top of the fraction. The good news is you do not need to do that chart method of figuring out the exponents. All you have to do is use the coefficients. So it does say that. If I could move this, but I can't for whatever reason, sorry. Okay, so we have products over reactants. And the exponent is just simply the coefficient. Okay, another big thing, and it is bolded there, no solid or liquid reactants or products are written in the equilibrium law. So if you think about trying to change equilibrium and reactivity, if you have a solid or a liquid, those substances are very, very, very unreactive. Liquid would be like water's a liquid, but we often we use it to make a solution, right? We make a solid ionic compound aqueous. So aqueous ions, they are able to displace and that kind of thing. So that's what we're looking for. You're only going to include aqueous substances, and then of course gases are also reactive enough as well. Solids and liquids, they are not. Can they be present in reactions? Sure, but they are not going to influence the equilibrium position because they're just too unreactive. Okay, so one of the types of questions you could be asked is about the size of KEQ. And you can think of it, if you remember that it's always products over reactants, then think of the math side of things and how a fraction works. So I like 1 and 4, okay? So if you have 1 over 4, that's 0.25. If you do 4 over 1, you get 4. So when you have a large number in the top of the fraction, then you're going to get a large number as your answer. When you have a large number in the bottom of the fraction, you're going to get a small number as your answer. So when K is large, when the ratio of products to reactants is big, then we call that being favored to the right direction. If you are directionally challenged, and I, people always giggle, but so many people cannot tell the difference between right and left. You can use forward and reverse. So right is forward, like what we're used to really, and the left direction is reverse. Okay, so when you have another way to say this, if the concentration of P is higher than R, or because products are always, always, always going to be in the top, and then we're going to get, that's like the 4 over 1 situation, which means that we say the forward direction is favored. So how do you represent that? You need to use a big arrow on top. Big arrow on top.
Can I go in?
little arrow on the bottom. Again, how big, how small, just make sure that I can that I can tell that you know the difference, okay? So however you like to draw your arrow, if you want to draw the reverse one on top, it doesn't matter. Just make sure that I can tell the forward direction is bigger, okay? And then the one that's a little bit cut off there, if K is equal to 1, there are approximately equal concentrations, and that is equilibrium, okay? And then, so then when K is less than 1, now we're talking about the 1/4 situation, for example. So now you've got a high concentration of reactants, or it lies to the left or reverse. Okay, so now the bottom of the fraction is larger than the top because, again, it's always products over reactants. So if you have a small number, then that means the bottom of the fraction is bigger. What's at the bottom? It's reactants. Okay, so they are favored. Sorry, that was terrible. Okay, and so the reaction lies to the left, or if you don't like left and right, the reverse direction is favored. And again, make your arrow big. So how big? It doesn't matter. So little arrow on top, or little arrow in the forward direction, big arrow in the reverse direction. Okay, so again, at the bottom there it says the subscript EQ has been left off of K in these general statements. This reflects the fact that there are other equilibrium constants. So whether this unit, this section, we're going to do KEQ. Next, we're going to do KSP when we talk about solubility. Then we're going to do acids and bases, Ka and Kb. So all of those are equilibrium constants. They just have this is like a little descriptor here at the bottom. Okay, so then it's describing the reaction you're doing. You could use K and not put a little subscript there. That's fine too. You could put whatever, K, Mrs. Todd, it doesn't matter, because all of the equilibrium constants are going to be products over reactants. Okay, so all these principles based on which is bigger, the top or the bottom, are going to apply to all of them. Okay, so let's do an example. So here's a reaction. So we're going to write the equilibrium law. So first you need to check that they are AQ. Not S, sorry. AQ or gases. So we have gas, oops. Gas. Wonderful. So they all are included in the equilibrium law. And then you're looking for the coefficients. They are going to become the exponents. And you want to do products over reactants. So in general, the K expression is products over reactants. If someday, somehow, we have real assessments, if you write this down, then you're not going to get marks for that. Not specific enough. Okay, you want to actually write out the equilibrium law. So we're doing concentration for now. So NH3 squared. Why is it squared? Because its coefficient is 2 over N2, which its coefficient is 1. So you can put that in or not. I'll write it in just so you can see it this time. And then H2 is 3. When you have more than one substance, sometimes students mess this up. The math you're doing down here is multiply. So you do need to follow BEDMAS, right? So you need to do exponents first, then you would have to multiply, and then you would do the dividing. Okay, so make sure you know what kind of relationship you have with your calculator so that you don't screw this up. I don't recommend that you use a phone if you can get a calculator at all. It doesn't need to be sine, cos, and tan. However, a scientific calculator with a display where you can use brackets is generally a good tool to help you be successful for these kinds of questions. Okay, so now in part B, it says if the concentration of N2 is 0.1 molar, and H2 is 0.02 molar, and NH3 is 0.6 molar, what is the value of KEQ? So now I'm just going to plug it in and then solve for this. In this case, solve for KEQ. You can solve for other. You could solve for one of the substances. It doesn't matter. So on D2L, there will be, I'm going to post a worksheet. So the solutions are already there, but obviously I can't hand the worksheet out because we are not at school. So I'll post the worksheet there as well. And there's also a checklist of questions from the textbook. So I recommend that you do as many as you can. This is pretty straightforward, but just to get to know the little picadillos about it, make sure you do it. Okay, so 0.6 is going to be squared, 0.1 is to the power of 1, and H2, is 0.02 squared. Cubed. Cubed. Okay, so you can decide how much work you want to show. Sorry, I had to write up here. I should have said that. How much work you want to show. You can show all of your work. You can, if you have a good relationship with your calculator, you can type all this in. I don't care if you use scientific notation or not. You should get 450,000. So then let's say we slide in a little C here. Which direction is favored. So now we have a very large KEQ. Which means the top of our fraction is big. So if the product is large, then that means that the forward direction or right is favored. Okay? Okay, so switching to equilibrium laws for if you have an all gas reaction system, then you could use partial pressure values. So P stands for pressure. It is the same principles, products over reactants. Oh, and I forgot to say this. Sorry, guys, let's go way back to the beginning. The best part of this is let's pick a different color. Let's pick a pink. KEQ has no units. None of the K's do, actually. So when you go back down to KP also has no units. That's very exciting. I forgot to say that. Okay. So that's good. Okay, so, and it's the same principles. You're going to do products over reactants. The coefficients are the exponents. So like I said, those little things are important fundamentals for every kind of equilibrium law we do. Law usually applies to a lot of things and it's definite, right? So that's why we're going to use that. So then if we look at the same example we just did, all of them are gases. Okay, then we wrote the equilibrium expression using concentrations. When you do partial pressure values, then we use P for pressure. Then we call it Kp, and we have the pressure, partial pressure of ammonia squared because of its exponents, coefficient, 1 for N2, that's its coefficient, and H2 is 3, and it's still products over reactants. Okay, so in the first question, a flask is charged with 3 atmospheres of N2O4 and 2 atmospheres of NO2 and allowed to reach equilibrium. Calculate the value of Kp. So if you remember from grade 11, ATM is just a unit for pressure. And again, I have to write my answer up here. So always, always, always write out the Kp or Kq, the equilibrium law expression. So this time we have NO2 and it's squared. And then we have N2O4, which is just the exponent 1. The pressure, partial pressure of NO2 is 2. Okay, so you just have to, again, make sure that you do the exponent first. I don't care if you leave it in a fraction. If you're, if you are thinking of math, that's fine. You can change it to a decimal as well. Okay, so the other type of question we can do with partial pressure is converting between Kp and Keq. So that's this formula here. Sometimes I refer to it as Kpeg, even though that's not a G. But then so that you remember that it's P and then EQ over here, it kind of looks like peg as opposed to the other way around. R is the universal gas constant, which is given. Okay, so this is, again, that's from grade 11. We're going to use the atmosphere form, not the 8.314, which was kPa. So we're always going to use the ATM form. You do have to make sure big T means temperature in Kelvin. So you're going to have to do degrees Celsius plus 273. And then this exponent up here, that stands for change in moles of gas. So how do we figure that out? You look at the difference between the coefficients, and again, you need to remember products minus reactants, not the other way around. Okay, so let's just slide in another example, because this really isn't difficult. You just have to, it's just, figuring it out. Oh yeah, okay, moles of gas of the products minus the reactants, and then it has to be based on the coefficients. Okay, so if this is our system and we're doing the change in the moles of gas from the products. So how many moles are in the products? There are 2. And then in the reactants, there are 2 plus 1. So you can have negative exponents, you can have a 0 exponent, you can have a positive exponent. There is all kind of variety, but it should be a whole number, okay? Because we're using the coefficients. So unless you've got a case where there's fractions, but that's cruel. That isn't a thing. We don't really do that in our questions. Okay. So now let's put it all together. So we're going to use the Kpeg formula to convert. So we have a temperature, and I'm using the same reaction, which I didn't write out here. Sorry. As before, we have the Keq value, and we're asked for Kp. So R would also be given. On a test or quiz. then temperature does need to be in Kelvin. Now, calculating the change in the moles of gas, maybe you could do in your head eventually. I'll write it out so that just in case you can, so then when you're looking back at your notes, you know where it came from. So again, you're doing products, which has a coefficient of 2, minus the reactants, which is 1 plus 3. So that's 2 minus 4, which is negative 2. No problem. Okay, then I'm going to write up here. Okay, so now we're going to plug in what we know. The hardest thing to these questions is really if you had to solve for KEQ and then you had to do a little bit of rearranging. You do need to do the multiplying inside the brackets here first before you do to the exponent negative 2. So it's just these two things to the exponent here. So do 0.0821 times 773 to the exponent negative 2, and then multiply by 6 times 10 to the negative 2. So just be careful of BEDMAS there. And again, if your calculator gives you an answer like this, that's fine. If you are into scientific notation, you can do that, but you don't have to. So you go 1, 2, 3, 4, 5 spots. I'm just gonna get rid of that there. Okay, but you can certainly leave your answer not in scientific notation, that's fine. Okay, so that's it so far for this first lesson. So I'll post, there's the homework from the textbooks already listed there, and then I will post the worksheet. The solutions are already there. I forgot that obviously I'm not going to see you to give you the worksheet. And then I will post an assignment that you can do that my first semester kids did last semester. And then but I need to figure out how to use the Dropbox so that I can easily give you feedback. So probably what you're going to do, even if you don't have a printer, you can just write out your answers on a normal piece of paper and then take a picture and scan. And it will, if you use TurboScan, it will make it a PDF and it's easy to upload. To be honest, I use TurboScan because obviously I don't have a photocopier at home, and it scans better than our photocopiers do at school. So please don't worry about the integrity of what your work is. I would never leave you out to dry. If there's something I can't read, then I will contact you and say, hey, can you resend that to me? If it doesn't work or it's too, like your phone's too old or whatever, then you can always just screenshot and send me a picture. If you're so inclined and you are like, no, I want to type it and type in calculations, if that comes up, then more power to you. You can certainly do that as well. Okay, so lots of variety. We're in this together, and really the hope is that everybody is successful. Okay, so I'll get right on that and hopefully set that up ASAP. Thank you. And if you have any questions,